Hello, welcome to this video where we're going to be talking about simulations and inversion for physical properties. So this is a case that we've been working with in YouTube Wells for a long while. It's based on a real case. Of course, this is synthetic data, but it's based on a real case. And the data that I'm using here is going to be also in the link in the description, in the folder that is there. And there's a separate exercise that you can do if you're interested in learning a little more. Practice makes perfect. Remember that when you get familiar with the code, you get to use it better. This exercise is going to be show you, the one I'm showing is going to show you how to work with thin beds or relatively thin beds, not laminations, just thin beds. That's why I want to make that clear. And the exercise that you have is going to help you work with invasion. So those are two of the most common corrections that you would want to do with UTEP wells. There's also anisotropy, and there's other cases where you want to do, but strictly with resistivity and strictly with physical properties that are the properties that are related one-to-one to logs. These are the most common cases. So in the previous exercise, we learned how to load the data, visualize it, and then populate the properties to have the poor man's Earth model. So now we have resistivity here. I'm going to make it a little thicker. The blocky logs, what we call the blocky logs that have the discrete change are the Earth model, and then the continuous line is the field log that we have. I'm going to make them both red just to be a little more consistent. I want to make this a little bigger so we know what we're looking at. Make it yet a little bigger because we're going to add another plot that is going to be important. And great, now we're going to do a simulation. To do a simulation, you can click here and you get the simulator for resistivity. We also have the simulator for nuclear logs, gamma ray, density, photoelectric factor, neutron porosity included. With density, you of course have density porosity. And we're not going to be going into detail here, but they work very similarly. And we also have for sonic logs, much easier, much more. It's very fast. It's a little restricted because it only works in vertical wells and layers are being perpendicular, but it's good in many cases. So in this case, it's going to be the resistivity. Here we just have the well that we're working on. This is fine. Then the tool is AIT, which is exactly what we want. And we have the variant Schlumberger 1D or 2D or SLB. We're going to use 2D just because it's faster. And we're going to do H model because this it matches better, or it's the tool that was used. Whether you use electrical permittivity or not hardly ever makes a difference. The borehole model can make a difference. We have three options. We have ideal borehole, no correction, or variant tool correction. If you click in that icon, it shows you the explanation for each one of those three. The ideal borehole is what you're going to use in most cases. It's basically borehole corrected. It's what service companies will give you in most cases. When you start doing things a little more in contact with the raw data, or if you just want to look into the principles of how the tool works, you go into the either no correction or variant tool correction. For now, this is okay. And it's going to be, you can change, this is going to be the log set where it's going to be placed, simulated. It's a good tag to have. And I'm just going to simulate it and let it run. While it's running, well, it's going to pop up the command window because it's an external program, in this case developed by SLB. And some of the programs are developed by UT, some are developed by other service companies. And now that it's done, we can see how that looks like. So I'm going to add it here. And now we have simulated logs. And I'm working with RT10, the shallower one. And you can see that the match is not perfect. In some cases, it's not bad, but in some cases, it's really not okay. So I have a couple of options. I can just modify this and then simulate. For example, I don't like this match, and I can run the simulator and see how that improves after that simulation. And that's good, but it would be pretty tedious to go one by one and maybe not as accurate. And it seems like something that can and should be automated. And yes, of course, it is something that can and should be automated, and we have that. So here we have a module called the MCMC module. It stands for Markov Chain Monte Carlo. And I'm going to close this. What it's doing is a Markov chain sequence of proposed models, so different resistivity models, and it's trying to match as close as possible the simulated and the field log. So we're going to use, these are the panels that you use. You choose which property. These are the properties that you can invert for. In this case, we're just going to stay with resistivity. If you want to constrain it, in some cases, that's a good idea. You can constrain it. You can invert for, in the case of resistivity and resistivity only, you can invert for formation property, invaded zone property, and invasion radius, which is something that you're going to do in the exercise if you do it. I hope you do. In this case, we're just going to work with the formation property, so we don't check any of the others. Then you decide where to initialize it. If you initialize it from the Earth model, it's going to take the properties exactly from where they are. Otherwise, it's going to make something similar to what populate properties does. It's just going to get a smart guess. Radius, we don't care because we're not inverting for the radius. This is exactly the same thing you were looking at in the forward simulator. It's just like a summarized simulator. And if you click here in settings, shows you the bigger window. Then you need to decide which logs are going to match with what. So because we are an AIT, we have RT10, and that's okay. And we're going to match it to RT10. So we're sticking to the shallow depth resistivity. And here we have the method. We have biased Latin hypercube, which is the one that I'm going to be showing. We also have quasi-Newton. They both give you pretty similar results. The assessment of uncertainty is different in those two cases, by the way. Biased Latin hypercube allows you to see non-uniform uncertainties, but it takes significantly more resources. The quasi-Newton is faster, but they're always symmetric. Both have, they both work pretty well. And then if you just care about the one solution, using the initial accelerator search is fine. And I'm going to use that only, which is going to finish at, I'm going to say 10 iterations. It's probably going to be less, or 2%. RMSD stands for root mean square deviation. And then there's some noise if you want to include it. Resistivity tool, induction resistivity tools usually have a 3% plus minus 5 millisiemens per meter. So I'm going to stick with that. And these are fine. These are more advanced options. And now I'm going to hit run. And what this is going to do is it's going to do something similar to what I was doing manually, but without any need for user input. Now we have 3 plots here that are going to give us a diagnosis. We have the misfit, and hopefully it's decreasing. And you can also see that the resistivity is changing at every iteration, and the match should be getting better at every iteration. We have the misfit. We have the RMSD. RMSD is just root mean square deviation. If you ever forget how to calculate it, it's we used to have an equation here, but it doesn't matter. So it's just the square root of one minus the other squared. That's it. And the misfit is very similar. So here's that equation. This is the RMSD, and the misfit, the only thing that it does is it has the noise underneath. So it's more accurate when you're doing numerical analysis. But when you the RMSD tends to be more intuitive, especially because the units are the same units you're working on. So it's a lot easier to compare. And then here we have the uncertainty, which we're not going to worry too much about it. But if you decide to calculate uncertainty, you should see this stabilize. So after a number of iterations, it takes about 100 iterations, so I'm not going to do it now. And now that it stopped, because now the RMSD is 1.8, great. Now we can see the results here. The match is pretty good. We want to get a little more greedy. We can do that here. We can go to 1. Now I'm going to allow it to go outside of the initial accelerator search just to see. I'm not going to finish all the way to the 100 iterations, but just to see how it looks like. We're going to try we're going to let it improve first, and then we're going to see where it can go. So first, you can see that it got worse, which is expected because we did not say take it from the Earth model properties. Had we said initialize from Earth model properties, we would have started in the endpoint from the previous one. So basically we reset it. We're going to let it run however many iterations it takes. After 4, we already are at 1.4%, and we can see visually that is pretty close. And because it's less than, no, we said 1%, so it still needs to get lower to get outside of the accelerated search. It may or may not get there. We'll see. At most, it's going to do 10 iterations like this, and then it's going to start showing us then it's going to start doing a local exploration to get the uncertainty. And to view the uncertainty, even though we're not going to get the best results for this, it's okay. You can go into the resistivity plot, and then you can see a heat map, and it should show here. It shows you more or less the options with the different probabilities. Most people would prefer to see just the confidence interval. Like I said, this is not the final result, but at some point it would get closer to that. Or you can just see the standard deviation. The confidence interval, you can modify that to whatever value. I'm going to stop this just so I can show you all those things. But now you can see that after, well, but yeah, by the way, you can also stop the simulation. And this is going to shoot up, and at some point it's going to stabilize. Now, let's see confidence interval, 9%, of course, not showing much. 95% is showing you something else. It's actually not bad. We can see that the uncertainty is being calculated. We would expect it to be a little more symmetrical. We don't expect them to be perfectly symmetrical, but that's this is fine. Not as unsymmetrical as this, although in some cases it may happen. And if you see it as standard deviation, they look, of course, symmetric, and it gives you a different idea. And that's it. I hope you get the most out of it, and go into the link, the folder that we have linked in the description to continue with the exercise where you can do something similar to this. You can redo this one if you want to. And we have the other one that is unguided, just with the few steps that we give you in the PDF, where you're going to be correcting for invasion. All right. Thank you. Bye.